So for example, well, just a summary, we were talking about adding and subtracting complex numbers. So you have to separate the real from the imaginary coefficients and then add or subtract those coefficients individually to get your imaginary sum or difference. So let's say we have 3 plus 2i added to 2 minus 2i. Two complex numbers here. What do we end up with? Well, we end up with, got to add the reals. 3 plus 2, that's this guy and this guy. Add that to 2. Then we're going to get a minus 2 here. So our result is 5 plus 0i, or 5. So sometimes when you add two complex numbers, you end up with just a real number, like 5. Same deal with subtraction. Or subtraction works the same way. Let's say you have minus 2 plus 2i plus 5 plus 7i. We're going to do subtraction here. So instead of plus, let's do minus. Well, keep in mind you'll have to distribute this minus through the relationship. So you can look at this like it's minus 2 plus 2i plus minus 5 minus 7i if you want. That's easier for you. If you do it in your head, you can do it in your head. So minus 2 minus 5 is minus 2 minus 5 here. Plus 2 minus 7. 2 minus 7 times I equals minus 7 minus 5i. Okay, next operation, let's look at multiplying. So suppose we have 3 times 2 plus 3i. Well, this multiplication, you would deal with it in the same way if you had 2 plus 3x. You distribute this 3 into the parentheses. So you would have 2 times 3 plus 3 times 3i equals 6 plus 9i. So that's a real times a complex number. What about a complex times a complex? 3 plus 7i times 4 minus 2i. Just making these things up. Well, there's two different types of terms here. There's the real term and there is an imaginary term. So you deal with this in the same way you dealt with when you were multiplying two factors together, like 3 plus 2x plus 2 minus 2x, 4 minus 2x or something like that. So we can use like a FOIL type approach. So we'll take 3 times 4 is 12. Then 3 times minus 2 is minus 6i. So it's like we did up here, but now we've got to do it twice. So now we do it to this one. 7 times 4 is 28, positive 28. But there's an I here, it's 7i times 4, so it's 4 times 7i is 28i. And then 7i times minus 2 is minus 14. But we have an I here and we have an I here. That's going to result in an I squared, minus 14i squared. So let's simplify this. So we get 12 28 minus 6 is plus 22i. Now minus 14 times, well, if I equals square root of minus 1, then I squared equals square root of minus 1 times square root of minus 1. Well, that just equals minus 1. So anytime you have I squared, it's going to turn into minus 1. Because if we took the square root of that, it would equal I. Square root of minus 1 equals I. So now this turns into a real number, minus 1, whenever you square I. Alright, so we have 12 plus 22i plus 14 now equals, I can combine these two real numbers, 26 plus 22i. So that's typically the case when you multiply two complex numbers. The outside term, when you multiply it, is going to turn into a real number. Now what about division? Yeah, division is a little unusual. You can't quickly, at a glance even, divide a complex number by another complex number. We're going to have to do something special here. And what we're going to have to end up doing is we're going to have to end up somehow getting rid of this complex number in the denominator and morphing it into a real number so that our denominator is a real number. And then it'll give us something that we can actually make sense out of. So if we start with this, then we want to multiply this denominator by something that will result in a real number. So we can do that with another complex number. We call this the conjugate of this first number, and the conjugate of a plus bi is a minus bi. There's just a change in sign here. So this is the complex conjugate, and you'll see, I will actually multiply this out. You'll see that when I take a complex number and I multiply it by its complex conjugate, you're going to end up with a real number. All the imaginary parts are going to drop out. So, but anyways, before we get to that, and I demonstrate that, let's fix this up yet. So if we put a number in a denominator, if we multiplied this by 1 over 4, we'd be changing it. We'd have to multiply it by 4 over 4, like 1. But we have to do the same thing with complex numbers. So if I multiply my equation over here by something with a denominator of a minus bi, I have to also do the exact same thing in the numerator. Now you got a minus bi over a minus bi, that equals 1. Any two numbers divided by themselves, any number divided by itself is always equal to 1. Okay? So now we've got to do the complicated. So division is kind of complicated. So now we've got to do multiplication in the top and the bottom here. And subtle difference in the multiplication. Okay, so in the top, again, we're going to do this the same way. C times A, C times BI. So we have CA minus CBI. Do this, and then this, plus dAI minus dBi squared, okay? In the denominator, I'm going to go ahead and do this. A squared plus ABI minus ABI minus B squared I squared. Notice now, ABI minus ABI will leave the denominator. And since this is I squared, that's negative 1, this term is just going to change sign, but it's going to turn into a real number. So you end up with, so I'm going to divide this into the real and imaginary portions up top here. Oops, that's going to really confuse everybody. Let's keep that in parentheses. Good distance away. So CA, and I'm going to go minus DBI squared, because I know that's going to turn into a real number, plus, then I've got dA minus CBI. So now I've got the real and the imaginary term. Then we have a squared in the denominator minus b squared, and then I squared is minus 1. Alright, so let's sort through these negatives here. So we got CA, now minus dBi squared. Remember, I squared is going to be negative 1, so this is going to be CA plus dB plus dA minus CBI. So we've got our real number and our imaginary and our complex number on top. And then on the bottom, we just have a squared plus b squared. As minus 1 times minus 1 is positive 1. And this is a real number on the bottom now. So now this all makes sense. And we could take this 1 over a squared plus b squared, and we can multiply it through this, distribute it through this, and through that if we wanted to. So the complex conjugate, every imaginary number has a complex conjugate. Let's look at some complex conjugates for numbers. Over here. So you can always do this division. So you have 2 plus 3i, the complex conjugate is 2 minus 3i, just that simple. If you have 6i, just an imaginary number by itself, the complex conjugate is minus 6i. So on and so forth. Do one more. 1 minus 4i yields 1 plus 4i is the complex conjugate. Let's discuss one last thing real quick. Powers of I squared equals minus 1. I cubed is I times I times I is I times I is minus 1 times I essentially is minus I. I to the fourth equals positive 1. You can try that for yourself. And then I to the fifth turns out to be I. So then you circle back through again. I to the 6. I to the 6 is minus 1. And this thing will end up going around in a circle. And that's why it's useful in engineering, complex numbers. I don't have much more time to explain this, but you can look into complex numbers online and polar coordinates if you want more information.